Yeah, see the screen, thanks.
So I figured it would be appropriate to call this talk Digesting the Digital Twin, because we're all eating. So expect some more of these jokes. The term here, digesting, is appropriate because we are breaking down the digital twin. And our goal of the talk is to summarize the work we've been doing together with Hal, Casper, Kenneth, and Peter. And of course, there's corridor discussions with the whole group. So it's hard to put all their names here. We won't get too technical, but the goal is to find the building blocks of a digital twin so that we can more quickly engineer digital twins. I'll start with the definition of a digital twin. It's important to try to define what this is because there's many different definitions out there, as you can see here. We picked a very general definition that was provided to us by Till and others working on surveying the digital twin literature. And the main goal is here that there is a two-way data flow between a physical asset, a physical object, and a digital object. So this is a fairly general definition. But we will, throughout this presentation, we will be clarifying what we mean by this. And hopefully by the end of the presentation, you will have the same view that we have on digital twins. So two-way communication, it's worth breaking that down into one-way communication first, and this leads to the concept of digital shadow. So a digital shadow is a one-way communication between the physical object, which we will call the physical twin, and a digital object, which we will call a digital shadow. What are the main benefits of this? Well, we can improve visualization. If we establish communication between a physical twin and a digital shadow, we can find better ways to show how the system is behaving in real time. We can monitor the system. We can do predictive maintenance, predict when particular component will fail or is wearing down. We can diagnose the fault, something happened in the system that's not normal. We can try to figure out what exactly has happened. And of course, general support for decision making. So throughout the presentation, I'm going to give small examples of these applied to a very simple example that we've built in the lab called the Incubator. Two-way communication. If we close this loop, we have a digital twin. And here the main benefit, it goes from being something that just shows a human operator information about the system into something that can autonomously reconfigure the system. And you see, this is opening a can of worms when it comes to complex physical systems. Of course, some of you might say this, okay, these are self-adaptive systems, SCADA systems, nuclear power plants have systems like this, that there's these feedback loops. So what is new about digital twin? So in our view here, it is more about a democratization of the techniques used to implement digital twins. And this leads to new interesting research areas, such as how quickly can we build new digital twins, and can we build frameworks that allows us to quickly set up digital twins for different use cases, different physical assets. And that is what we are trying to do research on. So I'll start with Incubator. It's a fairly simple system. Our goal was that it was very simple, that anyone could build it in their home if they want to start playing with digital twins. Here, it is comprised of a plant and a controller. The plant here is essentially has a heater, a fan, a couple of temperature sensors, the temperature sensor outside for the room temperature, and it sits inside a box. The goal is that you can place some content here, like yogurt, milk, to be turned into yogurt, and then you can set a controller to try to keep the temperature within the particular band. The controller, also very simple. We strive to have a controller as simple as possible so that we can highlight the benefits that the digital twin can bring by compensating for the simplicity of the controller. So this controller, here's a state machine of it. It has a couple of parameters. lower level temperature, upper level temperature. Then if the temperature is below the lower level, it turns the heating on. So it uses these MOSFETs to activate the circuit that activates the heater, and we are using a Raspberry Pi connecting via GPIO to turn these things on and off. So it turns on the heating, then it waits for H seconds before turning the heater off, and waiting C seconds before checking again whether the temperature has increased to the level it wanted, or then and repeating the cycle, or then going into a cool down phase. This will become clear why we have this simple controller when we see the simulations of this system. This is not a traditional bang controller. So let's see what are the atoms of a digital shadow. Starting with the communication. First and foremost, there are many different communication frameworks out there. We chose the protocol AMQP, of which we decided to use RabbitMQ as the implementation of that protocol. And for those of you not familiar with this protocol, you can think of it as Twitter for software. So the controller can send these messages periodically with some information, and then any subscriber can come in, subscribe to those messages, and receive them. If there's no subscribers, the messages are not kept. The messages are just deleted. The beauty of this system is its simplicity, maturity, and also openness, that anyone can come in, especially when we're talking about atoms of a digital shadow. We can add new processes to the digital shadow, and they can subscribe and get the data themselves. This setup was mostly developed by Casper and Kenneth. So visualization, the first atom, and a very important one, because in 5 out of 7 digital twin papers that Till has been reviewing mention 3D visualizations. And here the main challenge is ergonomics. How do we develop good visualizations for a particular system? Now, because this is extremely application dependent, for instance, if you're designing a digital shadow of a nuclear power plant, there's a lot of research into the ergonomics of such interface to prevent mistakes, etc., etc. So we set this out of our scope to delve deeper in this, but there are many frameworks out there that can be used to enable visualization the moment you have a communication framework such as RabbitMQ working. For our little incubator, just to give you a sense of what we placed, you can see we've used Plotly in Python. This is the same technology that's used in the INTO-CPS association app. And so it allows you to plot some stuff, omit some stuff, and so on. So here you can see, get a sense of how the system works. You can see we have two temperature sensors. Sorry, I hope this is too small. We have the heater is turned on at some point, temperature starts rising, and we have 2 temperature sensors inside the box, T2 and T3, and then we take the average of these temperature sensors, and of course we are also measuring the room temperature, the temperature outside the box. And as you can see here, this was an experiment of several minutes where we turned on the heater twice, and we observed how the system behaves. So let's start now with state estimation, and this is we start with this because it is the basis for many other atoms, many other small atomic processes that enable a digital shadow. State estimation, we will talk about the Kalman filter as one specific technique to do state estimation. And now a Kalman filter in our plant, the physical, in the box, we have at least 2 important temperatures. We have the temperature of the air inside the box and the temperature of the heat bed. That, sorry, I didn't show this more clearly. This is the heat bed. This thing gets very warm, then that heat is transmitted to the air surrounding in the box. So there's 2 important values, the temperature of the heat bed and the temperature of the air. And of course, We also measure the temperature on the room temperature. The controller knows when it's turning the heater on, but we don't have a temperature sensor for the temperature in the heat bed. So the controller can only emit messages containing a timestamp, the value of the temperature, the value of the heater, whether the heater is on or off, the value of the temperature, average temperature in the box, and the value of the room temperature. So the Kalman filter allows us to do two things. It allows us to, given a message like this, allows us to tell what the next temperature at 3 seconds later will be, temperature of the air inside the box, but it also allows us to recover what an estimate of the temperature 3 seconds later on the heat bed. And this is why this is called a state estimation technique. And it's important because it provides us the important state of the system. We cannot reason about this plant without thinking about the temperature of the heat bed, because neglecting the temperature of the heat bed leads to results, which we can show you later, leads to results that do not accurately mimic what's happening inside the box. You can think of this as, if you turn on the heater, this heat bed remains warm for a few seconds before it, and that's actually written in the label, that this thing remains warm for a long time after being turned off. So to do its job, the Kalman filter needs to have a model, and then uses this model along with the measurements that is receiving to predict the next state of the system. This is then used as a basis for safety monitoring, predictive maintenance, decision support, etc. It's a fundamental technique in the digital shadow that cannot be replaced. So we need to model the plant. We need to create a model of the plant. And this is what we did was, I'm not going to give you the equations, they're very simple. I'm just saying we built a model as a function that takes some parameters. These are parameters that characterize this particular plant. It receives the current state of the system given by the temperature of the heat bed and the temperature of the air, gives the state, the inputs to this plant, the inputs being the room temperature and the state of the heater, on or off, and tells us what the next state of the system will be 3 seconds later in this case. This model, because it has these parameters, it needs to be calibrated. So we need to run a parameter estimation process to find these values that best match the behavior we observe in the real world that's gathered from an experiment. So what we do is we run an experiment just like the one you saw, where we turn on the heater for some time and observe how the plant warms up, how the air and in the box warm up. Then we record this data. We then calculate, in this case, a moving average of the temperature sensors, because we are our model is supposed to give us the average of the air temperature and the temperature of the heat bed. We feed our model and the data into a least squares estimator, least square solver, and we get the estimate of the parameters that best match the data recorded. So this looks like this. After you've run this experiment, you should get a model that, starting from a known state of the system, gives you a pretty good estimate of where the system is going. So in this model, we started here by defining and assuming, again, we don't have a direct measurement of the heat bed, but we were able to assume that the heat bed is at the same temperature as the temperature of the air inside the box, thermal equilibrium. Then before we start the experiment, after we start the experiment, you can see that the model tracks fairly well without any further communication between the model and the real system. It still tracks fairly well what the system is doing. So this was a good result. Means we have a good model of our system, which we then can use to work with a Kalman filter. So the main difference, I have to stress, the main difference between the model And the experiment we've made so far and the Kalman filter is that the Kalman filter will continuously take measurements coming from the system and will continuously take them into account when trying to find the value of the missing state and predicting the next state. The model that we just did, we just were lucky because we started the simulation of the model at the state of the system that we knew. So we were able to provide a good guess for this value so we could start the simulation. This is what the Kalman filter does for us. We could implement other techniques like we did back in February or March, where we implemented the tracking simulator. This is essentially a batch least squares parameter estimation algorithm. And what this does is it periodically recalibrates the model as the data starts to diverge, and it records the some horizon of data and runs a recalibration on the model. And this can be run every 3 minutes, every 10 minutes or so. This is a technique that works mostly black box. You can any model, any function that tells me what the next state of the system will be can be used in this tracking simulator as long as I have the parameters for that function. And so this works for co-simulations very well. It can work to estimate both parameters and states, but at the same time, this is slow. This doesn't deal very well with noise without any extra filtering, and Kalman filter, despite the fact that it needs some linearization and manipulation of the model and knowledge of the model, this can be run very, very fast. So here's an example of how a Kalman filter can be used as a basis for an anomaly detector in the incubator. This anomaly detector would just see what the state of the Kalman filter is and compare it to the state, just the temperature of the air inside the box, compare it to the one provided by the actual control. And if the two start to diverge, something is wrong, because we know this model and these parameters, they accurately track the behavior of this plant. So something must have changed in the plant to make this model invalid. For example, suppose I open the lid of the plant. So I open the incubator. It's a styrofoam box that has a lid. At some point we can open this lid. So what happens is the model, the experiment we run to estimate the parameters of the model, it was run without opening the lid. So the parameters we found are for a scenario where the lid is closed. The moment we open the lid, the plant changes, and therefore there's more heat dissipation. And what we started to observe from the sensor is that there's a temperature drop that's faster than what the Kalman filter can predict. So even though the Kalman filter is getting constantly measurements from the sensor, it cannot track this behavior. And this is used as a basis for anomaly detection. The beauty is that the moment we close the lid, eventually things go back to normal. And we know, okay, we are again in the situation that is characterized by the model that we built to feed the Kalman filter with. This also gives us a basis to do fault diagnosis. A scenario for fault diagnosis would be to use different models representing a particular faulty scenario, such as the lid is open. These models can be calibrated through parameter estimation with separate experiments by opening the lid and finding these values there. They can be used to produce their own Kalman filters that most of the time, when the lid is closed, these Kalman filters are not going to work well. So they are going to work bad. They're not going to track the system, but the normal scenario will track the system. The moment we open the lid, this one starts tracking the system accurately, and this one fails. This gives us a way to diagnose the fault, because by using a bank of these models, we can at least build an estimate of what we think the scenario, the system is in. And this is used, there's other techniques out there like multi-model something to do this calibration, to do this diagnosis, but we are picking something very simple to avoid causing you too much, ruining your lunch. So we've seen how predictive, how fault diagnosis, safety monitoring can be implemented. Now we look into what is this? What do we mean by support for decision making? And here, what we mean is that we have a process that can be started on demand, and this process will take will run a simulation with a model and the parameters that we have so far. It will start from the state that's being measured in the system and then runs a simulation into the future. What is the use case of this? Well, for the incubator, a simple example is, suppose the operator is trying to wants to cut the power for some time, and he wants to know, okay, how long do I have to cut the power? So one way could be he runs a simulation with the current controller configuration, the blue one you see here, and he sees, okay, I have about this much time, but that's not enough. So maybe he thinks, okay, what if I can change the parameters of my controller in a way that will it will heat things a bit more next time, but and possibly break the boundary of the upper limit in the temperature. But maybe I can find a value for that parameter that will make it not break it too much, that I can gain a few more minutes to intervene. And this is what the what if simulation can be turned into a design space exploration problem to find a best new configuration for the controller. And in this case, for instance, the red arrow might be a value that's simply too high to be tolerated, but the green arrow might be a sweet spot where maybe the limit of the temperature is violated for a few seconds, but without causing any major damage to the content of the box, and is still allowing the operator to cut the power for more time. You might be wondering, okay, this is just a digital shadow, so finding the best configuration means you cannot automatically change the system. And this is where the need for the digital twin arises. It can enable automatic reconfiguration of the system when things change, which makes it a very powerful tool, but at the same time opens a can of worms, because whenever you allow, especially if you consider the system to be safety critical, and you allow self-reconfigurations from a digital twin, which is more or less an open-ended framework, there's several safety issues that that you have to be aware of. For instance, in our own incubator controller, we had to recode the controller to enable, of course, subscribe to topics. So not just the controller sending information, but also subscribing to topics in the RabbitMQ queue to listen for reconfiguration requests. But we also had to implement safety mechanisms hard-coded in the controller to make sure that the system is not driven into an unsafe state, such as these heating coefficients. They are still limited, upper limit. They are upper bounded. The limits of the temperature are also upper bound and lower bound. But this is because the processes on this side can become quite complex. It's fairly easy to have mistakes in them that then can lead to a faulty configuration of the controller. So that's the big warning sign we have here. For most systems, maybe getting a digital shadow will create enough value as it is, and that extra step of enable reconfiguration can be simply too high of a price to pay to get a digital twin. But our goal is, of course, to get a digital twin, and I hope I convince you that it's still worth it, the ability to do this self-reconfiguration. So the simplest example of self-reconfiguration is after running the what-if simulation, after running multiple ones, determining what the best configuration is. The best configuration is passed on to some component that passes on the configuration to the controller. Maybe this component does some safety checks before doing so, and then the controller gets reconfigured and uses the new configuration. Here's a more interesting example of a self-reconfiguration, and here what I want to stress is how these small atoms, which we've described so far, come into play to accomplish a more complicated task. So this is we want this algorithm to start when an object is placed inside the incubator. And here you can imagine I'm putting in there a bucket of cold water, extremely cold water, or a bucket of ice. Before, the system had a particular notion of what normal was. So the moment I place a bucket of ice inside the system, Kalman filter and anomaly detectors can be used to detect something has changed. After something has changed, we can schedule an experiment to gather relevant data. So we can, for instance, reconfigure the controller to let the plant cool down to some temperature, then ramp up heating for some time, so we can observe the response of the system during this interval. This is where the configurator comes in. Then the data recorder will collect the experiment being run, and we will use the least square solver to find the new parameters for the model. You can imagine we may have multiple models used, so this can be run for all models and then picking the most appropriate model to the new circumstances. We will then reconfigure the Kalman filter. This Kalman filter that detected that an object was placed, we reconfigure it with the new parameters, a new model. Then we are able to run what-if simulations to find to optimize the control behavior. And here you might say, why do I need to optimize the control behavior? Well, the controller parameters were previously optimized to deal with the fact that no object was in the incubator. Now we have a bucket of ice there. Maybe the heating, the age parameters that controls how long do we leave the heater on before checking how the temperature is moving. Maybe that can be changed now and optimized to prevent unnecessary switches of the controller of the heating on and off. So we run what-if simulations to optimize this controller behavior, and finally we reconfigure the controller. So, and we go back to the tracking the new normal of the system. Eventually the bucket ice melts, the water warms up, and then this system will start again because the object inside the box has changed. The circumstances have changed. So to summarize, so far in our research we have identified these atoms here on the left, where they can be used in combination to accomplish more complicated tasks. And one of the research questions we have are these enough to accomplish most tasks to establish a digital twin? Our second research question is, how do we now connect these together? Because so far we are using a scripting language along with these components, and we use them to accomplish the more complicated tasks. But it's easy to make mistakes, so we are wondering, okay, how can we best describe this orchestration of these different processes? And our main and third research question is, how can we then now apply the exact same, create a digital twin for other case studies? And the incubator was just our toy example. We have more complicated case studies at play. For instance, we have a UR robot arm, which we are developing a model together with Emil and Carlos, a master student. We have successfully found the dynamic parameters of such a model. So we have a model that can predict the current and torque forces of moving a robot. We are linearizing this model, for instance, so that we are able to do tracking using a Kalman filter to track whether something has changed with the robot. We also are working in desktop robotic. Casper and Birgitta will be working on safety monitoring, and they are using, for now they're using Gazebo and co-simulations. Matthias is working on indoor position tracking, so to be able to tell where the robot is indoors. And there's a couple of bachelor students who have recently built a more detailed and calibrated model of this desktop robotic. That's it. We have some other ongoing work, such as small enablers for some of these techniques in the digital twin, such as we have a tool that allows us to do a one-way communication into what-if co-simulations using, so that tool is called Rapid QFMU. We have worked before together with Christian, and Frederick and Peter on a tool and a tracking simulator that can be run in co-simulations and also can be run as a Kalman filter would be run together with the measurements coming from the system. And of course, there's a lot of other work that has not been published yet into injecting faults to create these anomalies so that we can train, find new models for these anomalies, and so that we can then do in practice fault diagnosis. And of course, we always have the challenge of ensuring that our co-simulations can run very fast, so that we can support what-if simulations where we run many different simulations in parallel in a design space exploration. That's it. Thank you all.